Okay, let's continue the second session. Second example. So previously we just show you a really simple case involving 3 variables. Now let's look at another example of mediation, basic mediation. So the data set is about active data. So it's short for advanced cognitive training for independent and vital elderly. It collected data from these 6 sites, and it just want to test the effect of 3 cognitive interventions on measures of cognitive demanding data activities. So we have memory ability, reasoning ability, speed ability. But again, we are not going to use all of these abilities. So let's look at the data set. There's a control group, there's an intervention group, and we have 5 trainings. Okay, the first assessment actually is a baseline is measured in the beginning part of the data collections, beginning part of the experiment. So we have the baseline measure, and we also have second measure, which happened immediately after the training. Okay, and then we have 3 to the 6 measures. Okay, annually after each year's training. So we have 6 waves. We have 5 trainings, and the sample size is large. Okay, but we're gonna use a small subset, include 1,114 participants, and the original variables are also the number of original variables also large, and we're gonna use some of them, 36 variables, and we have I just list all the variables. For example, gender, age, EDU, and the MMC. Okay, HVLTT 1 to 6 because we have 6 waves of measure. HVLTT is short for Hopkins Verbal Learning Test. Okay, and this test actually is for memory ability. So this is a memory total score. And we also have LS from 1 to 6. So LS is short for LED series. We also have 6 waves of data. And we have WS1, WS6 from WS1 to 6, so word series, and LT1 to LT6. These are for letter set task. Okay, so these 3 tests, LS, WS, LT, are actually for reasoning ability. Here we have some details of these tests. I'm gonna skip this part. And anyway, these are reasoning abilities, and HVLTT is memory ability. And we also have EPT. EPT is for everyday problem tests. Okay, so this is our dependent variable. So this measures the participant's ability to reason and solve problems associated with daily living, so daily life. So we have these variables involved in this model. So HVLTT is measure memory ability, WS, LS, LT are reasoning ability. And we're gonna also include the dependent variable EPT, okay, EPT here. And we have some independent variables. So we use age and EDU. We're gonna look at the inference of age and education level on the EPT. So of course, directly or indirectly through the mediator, memory ability and the reasoning ability. So that is our model. So let's look at this is the model we're trying to do the test. Okay, so we have age independent variable here. We have EDU, another independent variable here, two independent variables, and EPT is a dependent variable. Okay, by the way, we use the first wave of data because we have 6 waves. To simplify the question, we just use the first wave. And the mediators, look at these mediators. We have HVLTT, we have WS, we have LS, we have LT. We have 4 mediators. And first trying to look at the R code. And the data is called active.txt. Okay, also we have the header or the column names. So read the table, the file name here, the header equals true. And we're gonna pick those variables from the original data set. Original data set is quite big, so we're gonna pick H, EDU, HVLTT, WS, LS, LT, and the dependent variable EPT only. And that is the data, simplified small data set, okay, data for R. And then, okay, this is the first step, data preparation. And then specify our model. So again, we're gonna use a function called the specify model. Here, so let's look at this model, okay. This model here, the path diagram here is actually generated by the AMOS. AMOS is another software for SEM, okay. But we are not going to talk about AMOS in this workshop. Of course, AMOS is very powerful commercial software, and you don't need to do any programming. You just click those buttons and draw those objects, and it will automatically run the estimate for you. So we have so many paths, we have so many coefficients. Okay, look at this. So we have P1, P2 to P15. So we have 15 coefficients. And also we have a lot of variances. Okay, variance of age, EDU, okay. And the covariances. Look at this part, okay. So here we have age double-headed to EDU. So we have double-headed arrow here, but age, EDU are different. So that means it's a covariance, okay. Covariance between age and EDU. So here, and also we have some other, yeah, variance and covariance. Okay, those are variance, okay, variance. And in order to get the SOBO test, we again use a BMEM package, the function called the BMEM .SOBO. And we have the data file described here, okay, data file, and the model described here. And we have effects described here. Okay, let's look at this effect. What it is? This actually is, let's look at the first component. We have 2 components. Okay, the first component actually is a sum of different terms. So P2 times P12. So what is this? P2 is here. Okay, P2 here, P2 times P12. P12, where's P12? P12 here. So this is one specific indirect effect from age to HVLTT to EPT. Okay, this is one component, one specific indirect effect. But we're gonna continue. So we have the other component, okay, P2 times P11 times P13. What is this? What is this? This is another indirect effect. So P2 here, P11, this is P11, and P13. So this describes the mediation effect from H to HVLTT to WS to EPT. And we continue, okay, P3 here, P13, and P4. So actually, this is a sum of all indirect effect from age to EPT. So we just find all the possible indirect effects, specific indirect, and get the sum. This is a total indirect effect from age to EPT. And let's look at the second component. Okay, what it is? This is a one specific indirect effect. So P6, where's P6? P6, where's P6? I couldn't find the P6. Oh, here. Okay, I'm sorry. From EDU. Okay, from EDU to HVLTT. And then P11 here, and P13. So it describes the specific indirect effect from EDU to HVLTT to WS to EPT. Okay. And then after you use the Sobel test, so the total effect, total indirect effect, and the specific indirect effect will be reported for you. Okay. And of course, we use a summary to check the SEM result. So that's a code. Yeah, here, this is a bigger path diagram that gonna help us to look at the path easier. Okay. So all of these paths are described here. Okay, so just run the code, the R code in RStudio, and you have the output. So all of these are parameters defined in our model. So all of these, the black font path, okay, here it's from P1 to P15, and we also have S1 to S7 and the covariance between them, okay. So all of these are residual, okay. For example, LS to LS is a residual variance of LS, okay, and the covariance here, covariance between H and EDU. So all of these will be reported in the output part. And then we have two additional effects. So let's look at the first additional component. That is the total indirect effect from H to EPT, okay, from H to EPT. And the number is reported here. This is estimate, and this is a standard error, and this is a Z ratio, Z value, and the probability, okay, the P value. So based on the P value here, it's significant. So that means, what does that mean? So from H to EPT, the total indirect effect, okay, either, okay, from here, here, or here. Add them together, the total indirect effect is significant. And also look at the specific. This is from EDU instead of H. Okay, previously we checked the H. Now look at the EDU. From EDU to HVLTT, memory ability. So educational level gonna influence the memory ability, which influence the reasonability of WS, and which influence the dependent variable EPT1 is also significant because the P value here is tiny, and the estimate value, okay, report here, and standard error, and the Z value. Okay, that's of course, here you can modify this part. I just give you some examples of the effect. So you can just modify these paths, and you can add more components. Okay, you can change the path here. And finally, you define this as effect, and the M plus, not M plus, the R will run it for you. And that's it. These are just examples. Yeah, here we have degrees freedom 5, and you can, I think you can calculate by yourself. Okay, so here, how many independent variables? We have 7. Okay, 7 independent variables. So 7 based on the formula. Okay, 7 times 8 divided by 2. Okay, 28 number of information. And you're gonna also calculate all these number of parameters. And then get the difference. Okay, get the difference is 5. So that's why we have the degrees freedom 5. Okay, so that is R. So some people might complain that, okay, this code looks so complicated because we have to define each parameter here. For example, P2. What is P2? Okay, P2 is from P2 is from H to HVLTT. Okay, H here, HVLTT. This is P2. And define P3 and define all these variance or residual variance and the covariance. It looks complicated. Okay, so actually we have another package called Lavon. Okay, so now we are going to use SEM package, and later on I'm gonna show you another package called Lavon. Okay, and we're gonna use another package to the data analysis, mediation analysis. Okay, but first let's try to look at M plus. Yeah, so for the same model here, we have title, we have data. The data is called M plus EQS data because this data file can be also used for a EQS software. EQS is another SEM software. It's a commercial software. And for M plus and EQS, no column names are allowed. So that's why I remove the column names in the data set and save it to another file. And the variables, okay, inside the file, we have these columns. We have age, we have EDU, and we have mediators, and we have dependent variables. We're going to use all of these in the model. So I just copied all of this. And then model, okay, inside this statement, we define the mediation model. So HVLTT on H EDU. So in this case, we do not need to specify each parameter. Yeah, so in R, we just give the definition of each parameter here, okay, from P1 to P15 and to S7. And in M plus and also in Lavon, it's not necessary. Okay, we just use keywords to define those parameters. For example, HVLTT on H and EDU. So HVLTT here is regressed on. So remember, on is short for is regressed on. HVLTT is regressed on H and EDU. So we have two coefficients defined here. And the WS on these three. Okay, WS here is regressed on H here, EDU here, and also HVLTT, because memory ability also gonna influence the reasonability. So we have these three kind of like independent variables. Okay, so these are three causes for the WS reasonability, and also LS on these two. Okay, LS here is regressed on these two, and the LT is regressed on these two. Okay, some people might argue that, okay, I want to have a path from here to here. That's fine. That's okay. That's your model. Okay, you have to have a pre-assumed model. So in this model, we just have the as HVLTT to WS. Of course, you can also add the path here, add the path from here to here. And finally, so EPT, the dependent variable, is regressed on all of these variables. So we have H here, we have EDU here, and we have HVLTT, WS, LS, LT here. So it has all of these coefficient defined here. And then let's look at this part. We just have a name of variable, okay, H and EDU. What does that mean? Based on the table of the M plus, we want to look at the variance of H, variance of EDU, and also look at this statement is about width, okay, H with EDU. So the covariance between these two variables. So that means here, this covariance between H and EDU, and also variance of EDU, variance of H. So that is our model. And the residual, okay, some people argue, okay, where's the residual variance in R? We defined a lot of S value here, but in M plus, it automatically included, so you don't need to worry about the residual variance. And the model indirect gonna tell us the indirect effect or mediation effect. So EPT here, dependent variable, IND, okay, H. So all possible indirect effect from H to EPT. And the EPT, IND, EDU, so all possible indirect effect from EDU to EPT, okay. And in M plus, when you run the code here, yeah, you This is a revisit of the meaning of IND and the VRA. Okay, you have the result reported. So we have the model results. Here, all the coefficients are listed here. HVLTT on H, okay, that is P2, HVLTT on EDU, that is P6. Standard error, Z value, P value, and the WS, we have 3 paths, okay, and LS, we have 2, LT, we have 2, and for EPT, we have 6, okay, so 6 parameters, 6 weights are reported. And this is for the mean part. And then residual variance, okay. Mediators, this is mediator, and the dependent variable, okay. So we have 4 equations for mediators and 1 equation for EPT. So in total, we have 5 residual variance, and all of these are reported and is significant. And finally, let's look at the mediation effect. Because here we have 2 independent variables, okay, age and EDU. So we have 2 parts. This part is for age, okay, from age to EPT. All the related informations are listed here. And the second part is EDU, okay, it's about EDU, from EDU to EPT. And all the related informations are here. So let's look at the first part, from age to EPT. So we have total effect, which is a sum of total indirect, which is here. Okay, this is the total indirect, and the direct. Okay, direct is reported here, 0.014. Again, the number of this, the sum of these 2 numbers is a total effect. And this part is the specific indirect effect. For example, okay, from age to HVLTT to EPT. So this is one part of indirect effect. This is another part, okay? This is the third, the fourth, and the fifth indirect effects. And the sum of these 5 components is the total indirect effect. So you can see that the total effect actually is the negative. That makes sense. Because age, with a larger age, actually the EPT value should be less. Okay, if the people is older, get older, then the daily activity, the ability to deal with the daily activities should be lower. And let's look at the second part for EDU. Okay, educational level, total. Okay, total indirect, specific indirect, and direct. Okay, and then this one is positive. From educational level to EPT is positive. That also makes sense. With the higher educational level, the ability to deal with the daily life will be higher, will be greater. And it also report all the specific indirect is significant. Okay, all of these are significant. But look at the direct. Let's look at these slides again. So for direct effect from age to EPT, it's not significant. Okay, the p-value here is 0.520. So it is not significant. What does that mean? From age to EPT, the direct effect C prime, the C prime here is not significant, not significantly different from 0. So it is a complete mediation, okay? So it's a complete mediation. But for this part, direct effect from EDU to EPT is significant. This path P10 is significant. So this is a partial mediation. Okay, I think we have already covered the 2 examples. I hope that each of you will be, have some sense of the mediation. It's quite simple, right? So we can use either R or M plus to conduct the mediation test. Now let's look at the second session about bootstrapping. Bootstrapping is also very powerful. And here we use a Sobel test. And the standard errors are reported. Okay, standard errors are reported and the p-values are reported immediately for you. But in case, okay, the data are not normal, or in case the sample size is really small, then bootstrap method provide a very powerful tool. So the bootstrap method was first employed in the mediation analysis by Boland and Stein in 1990. And this method do not assume any distribution for the indirect effect A times B, because bootstrapping is very flexible. For any kind of like distribution, very weird distribution, it will have the bootstrapping distribution and it will give you a relatively normal distribution. Okay. So yeah, so this is we're gonna use a approximation of the distribution of A times B. And if we have small sample size cases, then bootstrapping is very useful for us. So let's look at the bootstrapping method. This method actually is to investigate the sampling distribution through the bootstrapping distribution. So in details, this method is kind of a resampling method, but with replacement. What does that mean? So once I draw an object from the population, the next time I still can draw the same object. So it's replacement, but the sample size should be the same as the original sample size, okay, with the equal size as original sample, and then obtain the statistic of interest. So for each resample, okay, we calculate the statistic of interest, and then we repeat many times. We repeat the resampling B times, the B could be really large, for example, 1,000 or 2,000. And then finally, we just generate a distribution of the statistic of interest, okay, so many times, and we create a distribution of that parameter or variable. This method is computational intensive. You can see that here with this step, we repeat resampling the data, and for each bootstrap sample, we calculate the statistic of interest. So sometimes it could be, take us a long time. It depends on your model. If your model is complicated, then maybe it will cost you some time. It's computationally intensive. And finally, we can get a distribution of a quantity of interest. So it's very useful when the theoretical distribution of a stack is complicated. Okay, sometimes we cannot assume it's normal. Then we can try bootstrapping method. Or the sample size is insufficient, it's not large enough, then we can use resampling method. And in most cases, we use bootstrapping to construct confidence intervals. Okay, confidence intervals. So let's look at the details of this. Suppose this is a population we want to investigate. Okay, and from this population, we draw a sample. Okay, this is a sample. The sample size is n. This is sample we obtained. And based on this obtained sample, we just draw a lot of like bootstrapping samples, resample of the same sample size. Okay, sample size n. We have a lot of like resampled small population, and then for each population we have one statistic, and then finally we created the bootstrap distribution of that statistic. Okay, so that's it. So we treat this one, actually we treat this sample as our population. Every time we draw the sample from this observed variable. And why do we have this bootstrapping distribution? Why do we want to use this distribution? Because we have a central limit theorem. Okay, central limit theorem. What is that central limit theorem? Yeah, so for this is example for X bar. Okay, so suppose we have, let's look at the details. Okay, if we yeah, so suppose that we have original X has any kind of like a distribution. Okay, no matter what shape of the population distribution of original X is, but when we draw many samples from that, when the sample is large enough, the distribution of sample mean is very close to normal. Okay, so the X bar, the original X may have very weird distribution, but the X bar, the mean of X, will be approximately normal. And what is the mean? The mean is mu. This is original mean of X. And what is the variance? The standard error. Standard error is, okay, sigma. Sigma is the original standard error of X, but X bar will be the sigma divided by square root of n. Or in other words, the variance will be the original variance divided by n. And this theory is called central limit theory. Okay, so the X bar will be normally distributed. Of course, it's approximately, okay, and with the same mean of X, but the variance becomes smaller. So the sigma variance becomes a sigma divided by the sample size. By using that theory, we can get the standard error of the estimate. Okay, based on this theory, we can have the standard error estimate, and then we can construct the margin of error. So critical value times the standard error of that specific statistic, we can have margin of error. And by adding the estimate, the point estimate, we can have a lower bound and upper bound to construct the confidence interval. Okay, confidence interval, the center point and the margin of error, which is a product of critical value, depends on the alpha level, and standard error, which comes from this central limit theory. Okay. And of course, you can also use a percentile method to, okay, again, we have the population here. So we can use a percentile to construct the confidence interval. So it's very useful for non-normal data, for small sample size, and it's intuitive and easy to implement. Okay, so I will just give you the details of the steps of the bootstrapping on mediation. But it's not a method to make your result more significant. It depends on your original raw data, original observed data, and cannot add information beyond your data. Okay, and of course, in R, there are a lot of packages. So next, I'm gonna introduce your package in R to do the bootstrapping on mediation. Okay. Almost run out. Okay, now let's look at the bootstrapping distribution of the parameter, okay, of the indirect effect, specifically in mediation analysis. So we have 4 steps. So we have step 1, 2, 3, 4. Of course, this is kind of the logic of the bootstrap method. As I mentioned, there are a lot of R package. You actually do not need to know all of these steps. So the R package provides you the final answer directly. But in order to help you understand the logic, I just show you the 4 steps. Okay. So first step, we have original raw data. Okay, we have the original observed data. So we treat that data set as our population, and then resample a set of data with the same n, the same sample size with replacement from that population or from that observed data. So we have 3 variables. So every time we draw these 3 variables from that observed variable, okay, and the sample size keeps the same, n. Once you draw a sample from that population or bootstrap sample, you run a mediation effect, or we run a mediation model. We run a mediation model and then get the coefficient of A times B. So the indirect effect will be obtained from each bootstrapping sample. And the bootstrap number of bootstrap sample could be large, okay, 1,000 or 2,000 samples. So finally, we repeat these 2 steps many times, and then we have the distribution of the indirect effect. Okay, so the B, the really large number is called the number of bootstraps. Okay, and finally, we have the empirical distribution based on that procedure, and that is a distribution of indirect effect A times B. Okay, estimate of the mediation effect, and we use that distribution, empirical distribution, to construct confidence interval. So normal based, we just described as normal based on the central limit theory. We can also use the percentiles. Okay, percentiles, for example, the alpha is the confidence level. So we have the 1 minus alpha times 100%. And we use the lower bound and upper bound percentiles to get the confidence interval. So in R, we're gonna use a loop. Okay, so we use for loop because here, the 3rd step, you have to repeat it many times. So we use a loop. We use a loop in R, and it's for, okay, in R. For different software, it has different command. In R, it's for. And now we are going to use a new package called Lavang. Okay, Lavang package to conduct bootstrapping mediation analysis. Oh yeah, first let's look at the code for the general mediation analysis in Lavang. So we have to define the model in Lavang. So suppose this is a syntax. So this is the name of our model. Okay, complete data. Later on, we will talk about the missing value issues. So we have another model. Let's look at this model. Okay, the same path diagram described here. And let's look at the math. Math is dependent variable tilde CP. What is CP? C prime times math. Math is independent variable plus B times HE. Okay, B is the one component of the independent indirect effect. HE. So this is the equation of math. We have coefficient, we have independent variables. Okay, and that is for math. We also have HE. Okay, HE is influenced by ME. So we have a coefficient defined here, A and ME. Okay, we use tilde. Tilde, what does it mean? It's kind of like an on in regression, in N plus, is for a regression model. And then here we have double tilde. Double tilde, what does that mean? Okay, ME, double tilde, S1, ME. So that is the variance part, okay? ME, and defined variance or covariance. And the name is S1. S1 is defined here. And HE double-headed, double tilde HE, and S2 is defined as variance of HE here. And we also have this symbol, okay? What does that mean? This is the define statement, okay? ID, independent effect, indirect effects. Indirect effects is defined as A times B. What is A, what is B? A, B are defined here, okay? This is a coefficient from ME to HE. B is a coefficient from HE to mass. A times B is defined as indirect effect, IDE. And what is the total? Total is defined as this equation, this expression. So C prime direct effect plus the indirect effect A times B. So these are two additional parameters. So we have the model defined in Lavin. So in previously SEM, we have to specify each parameters. We use one row to define A or B or C, but here we can combine some variables together. And yeah, this is explanation of all these symbols. Okay, in regression, we use one tilde to show it's kind of like a model, regression model. And the variance, we have double tilde or covariance if you have different variables. And the sign of this is actually is the definition, okay, definition of new parameter. Yeah, and C prime is here. Okay, CP is for C prime. That is a direct effect. And we have A times B, which is indirect effect. And the variance, okay, S1, S2, S3 are defined here by using the double tilde syntax here. And just like the code in the previous example, so we just run the code. And that is our model. Okay, this is our model. And then we have an SEM function for estimation. Okay, estimate. That is our model. Okay, this is our model defined here. And that is our data. Okay, data is ready. We have already imported the data to R, so that is our data. And then by using an option called bootstrap. Okay, bootstrap, this is a new option by running bootstrap confidence interval. So what is the number of what is the number B? 1000. Of course, you can change it to other numbers. So after you run this statement, the syntax, you have the outcome like this. We have math, okay, operation, okay, independent variable, two independent variables, and we have label, C prime and B, estimate, standard error, z-value, p-value, and also confidence interval, lower bound, upper bound. These are constructed based on the bootstrapping distribution. Okay, and this is a covariance, HEME, covariance, variance, okay, variance, and also this is variance. Residual, of course, is a residual variance because math is a dependent variable, and this is independent variable, okay, and total. Not independent variable, indirect effect, okay, indirect effect and the total effect, and estimate, standard errors, z-value, p-values, confidence intervals are described here. Let's look at the results. Okay, confidence interval for AB. Okay, AB here, indirect effect, AB, lower bound, upper bound, 0 is not inside this interval. So what does that mean? So it is significant. 0 is not included by this interval. So there's a significant mediation effect. So the conclusion is consistent. Okay, so previously we have the p-value. Okay, also here we have the p-value, which is significant. So yeah, we have p-value and the confidence interval to show together that there's a significant mediation effect. And for let's look at the total effect. Total effect here, the lower bound, upper bound, also 0 is not included. So we have significant total effect. Okay, so what does that mean? Total effect, significant. Indirect effect, significant. Let's check the C prime. C prime here, direct effect, Okay, lower bound, upper bound, 0 is not inside this interval, so it is significant. So the direct effect is also significant. So it is a partial mediation model. Okay, partial mediation model. Okay, that's for Laverne. We can also use M plus to get the bootstrapping mediation results. So M plus, we have title, we have data, we have variables, we have analysis of variables, we have names, we have use variables, we have analysis. Here, you have to remove this exclamation point. Okay, so after you remove this symbol, the bootstrapping will be employed, and the number is 10,000. Okay, it's much larger than, yeah, it's up to you. So this number could be 10,000 or 1,000. And then let's look at the model. Okay, HE here is regressed on ME, and the path is specified as A. Okay, so this is a name of A, the coefficient from ME to HE, and also math on HE and ME. So we have different names. Here we have B, here we have C prime. Previously, okay, we used, in the previous example, we use, let's look at the code here. We use model indirect. This is one way to get the mediation effect. We can also use another statement, which is described here. We define some new variables. It's called model constraint. Okay, after this statement, we can have some new variable defined. So new, we have direct effect, we have indirect effect, we have total effect. So what are these effects? So the specific mathematical form is defined here. Indirect equals A times B. What is A? A is defined here, okay? And B is defined here. So A times B is defined as indirect effect. And direct effect is CP. What is CP? This is C prime, okay? It's the direct effect from ME to math. We also have a new total variable defined as a sum of C prime and A times B. So we defined 3 new variables, and we use a model constraint in the M plus to allow the M plus to show the results of these 3 effects. And outputs, of course, if you remove the exclamation symbol, so you have the confidence interval constructed. Okay, so we use a BC bootstrapping method. Bootstrapping method, confidence interval, we have series method. BC is just one of them. We also have BCA or some other improvement methods. So confidence interval. And then we have the result reported. So number of free parameters, we have, IC values, we have IMSEA, CFI, TLI, okay. All of these models are actually saturated. Okay, here we have saturated models. So that's why the model fit is perfect. Okay, so we have 0 here, we have 1, 1, 1 here. And then we have the model result. Okay, so these are parameters. The bottom part of the model result, we have 3 new variables reported here. So direct effect, indirect effect, and the total effect. So these are estimate, standard errors, Z ratio, and the p-value. Okay. So again, if you look at the indirect effect, it is the p-value is less than 0.05. It is significant. Okay, and all of these are significant. We can also look at the confidence interval by using the bootstrapping method. So here we have coefficient, for example, HE on ME. This is what it is. This is A. This is the path A. HE on ME. A lower 0.5%. Okay, lower 2.5%, lower 5%, and estimate. This is a point estimate, and we have upper bound So all the percentiles of the bootstrapping distribution are shown here. And the math on HEME. So yeah, this is a B, this is a C prime, and the mean, intercepts, variance, and also new. These three new parameters. And the lower bound, okay, the upper bound, the point estimate are all based on the bootstrapping resampling method, bootstrapping distribution. Okay, so that's for bootstrapping method. Now let's look at missing data. Okay, missing data problems. What is a missing data? What's the definition? Okay, data are missing on some variables for some observations. Really simple, okay? And the missing data are almost everywhere. And for example, if you have studied pre-test or post-test, some students just disappear in the post-test, okay? So they just attend the pre-test and no scores for post-test. So we have missing values. So we have some dropouts. So we have different patterns, for example, or forms. We have intermittent missing data. For example, sometimes we have missing values here. Okay, yes, that means, okay, the third observation is missing, but then that person or that value comes back, okay. But we also have dropout, so that means it disappears always, okay. After that 10 points, okay, all missing values. And later in the looping give us 3 data mechanisms, okay, because in order to model the missing data, we need to know the missing data mechanisms. So basically we have 3 mechanisms. One is called MCAR, which is for missing completely at random. Okay, missing completely random. So it is independent on both observed and unobserved outcomes. It just completely at random. For example, if the post-test, some people just disappear, then if the missingness is independent of both pre-test or post-test score, then we can see that missing mechanism is missing completely at random. We also have second mechanism called MAR, missing at random. Missing at random. The missingness depends on observed variables, but not depends on unobserved variables, unobserved outcomes. For example, again, in the previous case, if the dropout is due to the low pre-test score, so some people attend the test and after the pre-test, the score is really low. So the pre-test is observed, but based on the observed pre-test, that person decided to not take the post-test. So that missing is called MAR, missing at random. Based on the missingness is based on the observed information, the pre-test in this case. But we also have missing not at random, NNAR. So what does that mean? The missingness depends on some unobserved information, unobserved outcome, or some unobserved, some latent variables. Then we call it missing not at random. For example, the dropout is due to the fear of potential poor performance on the post-test. Okay. If the person, yeah, just don't want to have the poor score and the post-test is unobserved because it's not taken yet, so it's unobserved. But because the missingness due to that potential value, the missing is called missing not at random. It depends on some unobserved outcomes. But for missing at random, the missingness depends on some observed variables. But if the missingness is independent, okay, it depended on both observed or unobserved, then we call it missing complete at random. So we have 3 cases. If you really want to model the missingness, you have to know this mechanism, and we'll have different models set up. So missing data problems is how to analyze when data have missing values. So we have some goals. We're trying to minimize the bias. We're trying to maximize the use of the available information, okay? And also we want to get good estimates of uncertainty because of the value is missing. There's uncertainty of that value, okay? So we're trying to minimize bias. We're trying to maximize the use of available information. We also want to get good estimate of the uncertainty of that variable. So it's not a goal. What is not a goal? Impute the value close to the real value. This is not our goal. So some people just use a simple imputation to replace that space, replace that missing values. Actually, that cannot provide a very good uncertainty. So that is not our goal. Of course, we can use multiple imputation. The simple imputation is not good, but multiple imputation is a good approach. So traditionally, people use some really simple ways to deal with the missing values. For example, listwise deletion. Listwise deletion, what does that mean? If I found one missing values is one case, then that whole case will be removed. Okay. In many ISDSA model or in some R functions, so they just do the listwise deletion. So listwise deletion provide lower power biased estimate for MAR or NAR. For missing complete at random, it doesn't matter. But for missing at random, missing not at random, so it may cause biased estimate. But unfortunately, this is very widely used in social science. People just delete the whole case. So some information just lost. So we have lower power. So we suggest some other method, for example, full information likelihood method. So FIML, so full information likelihood estimation method. So basically, we're trying to use all observed information, okay, all observed data points. And of course, the details of this method involves the likelihood function of all observed data points. And then we can just trying to use EM algorithm to trying to do the estimation of the statistics, the parameters. We can also use MI. MI is short for multiple imputation. As I mentioned here, imputation, we have two ways: simple imputation, single imputation, and multiple imputation. Single imputation is not suggested, but multiple imputation is good because it actually is trying to impute that place, the missing values multiple times. It create the the variance of that variable, okay? It considers the uncertainty of that variable, okay? Again, we didn't look at the details of this procedure, but anyway, these two methods are good suggestion for dealing with missing values. So specifically in mediation analyses, as I mentioned, okay, traditionally people just use the listwise deletion, for example, the analyses. But we can try to combine the bootstrapping and the missing data methods to do the estimation to provide better estimates. So these are steps in this procedure. Let me see, now it's 10:20, so we needed to hurry up. So we have 4 steps. The first step, just like bootstrapping method, okay. So we treat the original data set as population and we draw sample, bootstrap sample from that population, and we create a mediation. With the bootstrap method, we estimate model parameters of mediation effect by using MI or ML for information maximum likelihood estimation method to deal with the missing values. And then these 2 steps will be repeated many, many times okay, B times. And finally, we got the empirical distribution of model parameters, okay, that combine the bootstrapping method and the missing data methods. So let's look at the example. So suppose we have 3 variables. Okay, so in this case, we have some missing values. For example, here, the third variable of the second case is missing. Okay, the second value of the third case is missing. Okay, so all of this NA means missing values. So this is not complete data. So the data set is called NLSY.miss. So we just drop some values from the complete NLSY data set. And when we use Lavon package, luckily, so the Lavon package will automatically take care of the missing values. So in the SEM, estimation, this is a function, okay, function to estimate the parameters. So SEM, we have model specified, we have data set, and we have bootstrapping option. And then we have another option for called missing. Okay, missing, we can have the option FIML, full information maximum likelihood estimation method will be employed. And the missing value will be will be dealt with. Okay, so yeah, these are details explanation of the missing option. So we have some other options. So I'm gonna show you the example in R. So after these slides, so the result will be obtained after we run the R code. The output, just like this, we have some, okay, these are names. Up by adding miss, that means, okay, the data set is, the data has some missing values. And the C prime missing value, okay, B missing value, AM, S1, S2, S3, all of these have some missing values in the original data set, but we have finally get the estimate. Okay, estimate the standard error, Z values, P values, the lower bound, the upper bound, based on our bootstrapping method. And also we have the IDE, indirect effect, total effect, okay, defined here, and the estimate and report it. It is, again, it is significant because the confidence intervals, okay, does not include a 0. Okay, it's significant. It is significant, although there are some missing values. After we use the maximum likelihood estimation method, the final conclusion keeps the same, still significant. So in short summary, we just use a Sobel test to test the A times B simultaneously, not separately. We also use a bootstrapping method to construct the confidence interval of A and B to test if it's significant or not. And for missing values, we can either use maximum likelihood estimation method, or we can use a multiple imputation method. And luckily, the R package, Lavon package, deal with the missing data values easily. Okay, so let's look at the code. Let me show you the code. This code is for the complicated mediation. So maybe I'm gonna skip this part. So we have the same package, and we have the active data, and we just get the small subset from the original large data set, and we specify model. We define the model here, and then we have the effects. Okay, the total effect, total indirect effect, and the specific indirect effect. So you can have many definitions here. And finally, we use Sobel test to do the mediation model analysis. So finally, we have the result. Okay, let me just run it quickly. So we have this, and all the code will be available for you. And this is our model. And suppose we are going to look at the effects of this one. And the second example, yeah, by using the summary, we have the result reported here. By here, if you look at the code, I also add some other model evaluation model fit indexes here. Okay, by adding the fit indexes, and all of these will be reported in the model fit indexes in the result here. Okay, so in addition to AIC, BIC, which are very simple, we also have the GFI, HFI, adjusted GFI, and the NFI, NFI, all of these model evaluation indexes. It can help us to tell if it's model good or not. And the final result. And let's look at the mediation bootstrapping method. Okay, bootstrapping. So we're gonna use a Lavang package. Okay, so you should install the Lavang package first. So I have already installed it. So where's the Lavang? Yeah. Let me see. SEM. Previously, I have the SEM package. So SEM and the Lavang package are the same, the similar SEM package. So in order to use one of them, you can just detach the other one. So I uncheck this one and then detach the SEM package. And then I use the Lavang package, highlight this part. You can also check the Lavang. So if you find the Lavang package here, then you can check that. And working directly, I use the same working directly. So the data, yeah, this data set is a complete data set. So we use a read table to input the data set into R. And that is available for us. Okay, the data set is called analyses complete. Okay, it's available for us. And this part tells us the logic of the bootstrapping method. Okay, it just shows you the details, but you can totally ignore this part because we have the package, we have the Lavang package. So we have the Lavang and we define the model first. The model has been explained in, yeah, when we talk about these slides, we have already explained each command here. And then we use SEM command to find the distribution, bootstrap distribution of A times B. Okay, bootstrap 10,000, the 1,000, and the SEM use the bootstrapping.
Hi, Dr. Lu.
Yes, yes.
I think the slides. Is frozen, so I can just see the multi-level mediation slide. Yeah.
Thank you. I forgot to change the share screen. Sorry. Yeah. So I'm sorry. So let's go to the RStudio. Yeah. Now can you see the code?
Yes. Yes.
The code? Okay.
Great.
I'm very sorry. I forgot to change the screen. So let me just look at the bootstrapping part. And this is a Lavang package and the model described here. And the SEM. Let's try to highlight this part and just click run. We have the result described, shown here. So it's still running. When the red sign, okay, now it's good. Okay, so when the red stop sign is shown, that means okay, it's still running. Running is a bootstrap distribution. So finally, we have the parameters from the bootstrapping method. Okay, C prime, B, A, S1 to S2, S3, and the indirect effect, total effect. And if you really want to try to look at the bootstrapping method, you can have this part. So the B, the number of bootstrapping is defined 1,000. And here we just defined space for the bootstrapping. And the for is a for loop, okay, for loop. So we just repeat this procedure B times, 1,000 times, and we have seed. Yeah, you can just ignore this part. Seed will make sure you have the same result every time. Otherwise, the system will just assign you a seed and you cannot repeat the same result. And we have we have sample and 1 to n. Replace true. Okay, replace true. What does that mean? So every time I can draw the same object from the population, replace with replacement of true. And sample size is n. Okay, this is a sample from the population. And then we create this index. This index just draw the objects from that population. We draw the ME, we draw the HE, we draw the math from the original observed variable. And then we run the linear model. Okay, so this is the equation of HE depends on regress on ME. This is a regression of math. Okay, linear model LN, it's a regression in R. So math is regression on ME and HE. And we have some coefficient. Okay, so we use a $sign to pick the specific parameter from the output. We have $sign. So after you run these 4, we just create the distribution of the indirect effect. And this is a histogram. Okay, histogram is a function in R. We're trying to create the histogram of the bootstrap ABO. Okay, it's the indirect effect of, and the confidence interval. Okay, confidence interval, percentile or the normal based confidence interval. So these are formulas, critical value and the standard deviation. This is empirical standard deviation. So that's why it's the standard deviation of the whole distribution or the bootstrap distribution. Okay. And of course, this is minus plus the lower bound or upper bound. This is the point estimate. And we can also use a percentile to construct the confidence lower bound and upper bound. So percentile, the whole distribution here, and we decide the alpha level, okay, alpha level here. So finally, we can just run this, and we have the histogram plot of the A times B, indirect effect, okay, indirect effect. Also, we have the confidence interval. So if you want to check the details, you can just here. This is the lower bound, this is the upper bound based on the central limit theory. Okay, and we can also use a percentile to construct the CI. And it is here. Okay, it's not exactly the same, but yeah, but it gives us the same conclusion. It's significant. So it's significant. So that's for bootstrapping. And then let's look at the missing values. Missing value. So we have a new data set including some NA. So missing values in the original complete. So we just delete some values from the complete data set. We call it the analysis miss, okay, miss. And then, yeah, you can check the new name. So now we have a new name, new column names by adding miss for these 3 variables. And we have some NA included here. So N row, number of columns, sample size, the same, 371. And this is a proportion for missing values. So if you use sum of so this is the complete cases. In total, we have 262 complete cases. And if you want to calculate the proportion of the missing values, then there are almost 30% of the values are the cases are missing, have missing values. And then we have the model of the mediation effect. Actually, the same model. Okay, the model, we just use different variable names, but the structure is the same. So let's highlight this part. And then let's try to use a maximum likelihood estimation method to deal with the missing values. So still we use SEM, and the model here, described here, the data is here, okay, data here, and then standard error using the bootstrap method. Okay, bootstrap number is 1000, and the missing value, okay, missing value method, FIML. And then we have parameter estimate. So we from the outcome, we just look at the percentile. Okay, we just construct the confidence interval here. So let's just highlight this part. Still, yeah, it's running because there's a red stop sign. The R is still running the bootstrapping. Let's wait for a while. It will be very quick. Yeah, it is still running. Okay, now that is the outcome. Okay, we have the estimate of all of these parameters, and we have the indirect effect, we have the total effect. It is significant, okay, by looking at the confidence intervals, or you can look at the p-values, okay, it is significant. All of these are significant. And the C prime here, it is also significant, so it is a partial mediation. That's for the bootstrapping. So let's go back to the slides. Let me just finish the advanced mediation models. So let's look at the multi-level mediations. Multi-level mediations. So in many cases, the outcomes are not independent. Okay, previously we assumed that the residual errors part are independent, but if these assumptions violated, then maybe we cannot use a traditional mediation model. So there are many cases we have structure or nested structure. We have multi-level structure or nested structure. For example, the students are nested within classrooms, and the classrooms are nested within schools. Okay, measures from the same individual are nested within the same individual, same person. So all of these indicates that there's a multi-level structure, hierarchical structure. Okay. So some units are nested within other level of units. Okay. The samples are not independent. So in that case, maybe the traditional mediation is not a good approach. Instead, we needed to use multi-level models. Okay, so basically we have different levels. So for example, we have student level, we have classroom level. If students are nested within classrooms, so usually we call the students is level 1 or lower level, and then the higher level, level 2, this is a classroom level. Or students are nested within instructors or teachers, professors, then we have different levels. And for each level, we have their variables, okay. So this is one example. So within a school, we have different classrooms, and within each classroom, we have different individuals. So yeah, so the errors in this case, the observation in this case are not independent, okay. Then how are we going to modify the traditional mediation model to have better or more accurate result? So let's have a revisit slides. So by including intercept, so previously we just ignore the mean part. now if we suppose we have intercept or the mean part for each equation, then the two equations will become this. Okay, so M here, this is a moderator, have the intercept and the A times B, and of course the residual of the M. And the equation of M becomes this by adding the intercept of Y. Of course, we have the residual term here. Okay, and the C prime is still the direct effect, and the indirect effect is A times B. If we have the simple linear regression, we have this equation by including the mean part, the I part. I is a total effect, total effect. So when the assumptions of independence is violated, we can consider some other new models. And if we still use the old model, traditional model, we still have some results, but those results are biased. Okay, those results are not very accurate. And also the standard errors and the p-values, the conclusions will be not accurate. So let's consider a multi-level approach to the mediation analysis. So in that case, let's look at some really simple mediation, including two levels. So we have level 1, level 2, so variables at the level 1. So we use I to show, for example, this is the individual, okay, I, individual at level 1. And then we have a higher level at level 2. So we use a J to denote the higher level unit. So for the same level 2 unit, so for the same unit, level 2 unit, all level 1 units have the constant value. Okay, for example, professor or the instructor. So for the same class, so all the students share the same instructor at the same level 2 unit. Although the individuals are different, but their instructors are the same. The constant for all level 1 units nested with under a level 2 units. And let's try to modify the coefficient a little bit. So for example, if A is constant from A to Y, so we have this coefficient A. But if it's random, what does that mean? If it's not constant, because we have level 2, okay, what does that mean? So for one classroom, we have a fixed value, for example, coefficient, but we have multiple classrooms. For each classroom, we have their coefficient. For example, here we have A. So we have A1, A for classroom 1, A for class 2, A for class 3, A for class 4. So we have many A's. That A can be treated as a random effect, random variable, instead of constant. If we just consider one classroom, then that coefficient A or B or C is fixed, is constant. But now we have multiple classrooms. So the coefficient A or B or C becomes a random. So we use this to show, okay, is a random effect. And we add J. So what does that mean? Based on different J, different level 2 unit, the A value will be different. It is a random variable, okay? It varies between level 2 units. And now, in this case, all the coefficients A, B, C could be different at different levels too. So if you think about the classroom, so classroom 1, we have A, B, C, A1, B1, C1. Classroom 2, we have A2, B2, C2. Classroom 3, we have A3, B3, C3. And if we have multiple classrooms, so the A, B, C are all random variables. So we use AJ to show these are random variables. So in this case, X, M, Y all at level 1, and from X to M, the A is random. Okay, A coefficient is random. From M to Y, the B coefficient is random. And from X to Y, the C prime direct effect is a random variable. So in this case, how are we going to model our equation? So we have two levels of equation. Level 1 equations, just like the previous traditional mediation, okay? we have M, okay, comes from the intercept and the inference of X. So all of these variables quite looks quite similar as the previous syntax, but we do have J variable, okay? So I and J. I is for individuals at level 1. J is for level 2 units, okay? And we have IJ. D, we have mean for J. So what does that mean? So the intercept will be different across level 2 units, but for the same level 1, it is the same. Okay, when you fix J, this value is the same. And also for AJ, A, when you fix J, when you fix the classroom, the A value is fixed, but the J will be different across different classrooms. So the AJ will be different. And we have the X, this is the independent variable, and then we have the residual. The same for the second equation. All the coefficients here, okay, we have J subject, J subscript, J subscript, B for J subscript, and also the mean part, we have J. That is a level 1 equation. We also have level 2 equation. What does that mean? We can get the average of all the random effects. For example, I can get the average of the mean of M. I can get the average of mean of Y. I can get the average of A random variable coefficient. I can get the average of B, J, okay, and get the C prime, which is average of CJ prime. So we have level 2 model. Level 2 model. It's kind of like a summarize the random variable coefficients A, B, C, and also their intercepts. And we have the residual part. In addition to the average part, we also have the residual part. By combining these two parts, we have their random effects. So that's a multi-level mediation model. But how are we going to conduct the actual data analysis? So that is a code, okay? So suppose we use M+, so this is M+ code, yeah. So we have title, we have data, we have variable, okay? So here, this is a name of all of these variables, available variables inside the data set. We are going to use some of them, 3 of them, okay? Use variables are X, M, Y. X independent variable, M mediator, Y is a dependent variable, just 3 variables. And then we need to add some other keywords. Cluster, what does that mean? Level 2 units, okay? Level 2 units, because for this data set, we have many individuals. Within each individual, we have some measures. We have measures of X, measures of M, measures of Y. So the cluster is subject ID, level 2 unit. And then we have some other keywords within. Okay, what does that mean? The X here, the X variable is within, okay, independent variable within. And these are dependent variables, okay, dependent variables, yeah, so we have to describe the independent variables within or between. We also have between independent variables. So let's look at the code. So within independent variable, okay, Rx, you can change it to between. Sometimes, yeah, in the next few slides, I will show you another model with X at independent variable at level 2 unit. But in this case, X and Y are all at level 1. So X is within. And then analysis. So here, this is a new thing for multi-level mediation. So we need to add type 2-level random. What does that mean? 2-level. This is a 2-level model, level 1 and level 2. Random. What does that mean? Random slope. Intercepts are random, automatic included, okay? So we also have random slope. And then let's look at the model. Inside of the model, again, we have 2 parts, within part and the between part, okay? Within part is about the equations of level 1. So let's go back to the equations of level 1. So here we have equations for M, we have equations of Y, and we have A, B, C. All of these are random coefficients, random slopes. And then inside the within part, within percentile, we define 3 random coefficients. One is A, one is B, one is C prime. All of these are random slopes, okay, random effects. And we use a vertical bar and the name before the vertical bar to define a new random variable. So A is defined as random, and A is a coefficient of M on X. What does that mean? M mediator is regressed on X. So this is a coefficient from X to M, and it's random, and the name is A. Okay, similarly, B vertical bar, Y on M. Okay, B coefficient is random, and it's from M to Y. We also have C prime, okay, C prime, Y on X. So these are 3 random effects at level 1 within, okay, within level 1. And then we have between part. Let's look at between the second equation, the level 2 equation. So we have average of intercept Y, okay, average intercept of M, and average of A, B, C. So by using brackets, we define the average. Remember in the table, in the keywords, by adding a brackets, we define average. Okay, the average of A is called MA, mean of A. So we have a new name for that, the A bar. And the average of B, the mean of B, we define as mean MB. C prime, bracket, okay, average, we define it MC. And then we also have some covariance, okay, A with B, covariance between A and B, A with C prime, okay, B with C prime, we have covariance among them. And the mean part, so the covariance actually is here, okay, so we have covariance here. We have variance and covariance, wait a minute. Yeah, these are variances. And if you put name A, B, C prime, it also will estimate the variance of this part. And then model constraint, by using this, we define some new variables in M+. Remember, okay, in the previous example for traditional mediation, we also have model indirect, but that statement will not work for multiple mediation. For multiple mediation, we use model constraints. So the model indirect statement will not work in the multi-level mediation. So we define new direct and indirect, and direct effect, the mean of C, okay, and indirect effect, the mean of the A times mean of B plus the covariance of A and covariance and A and B. This due to the theory part, okay. So AB, if they are not independent, so the expected value of AB, so, or the average expected value of A times B is the expected value of A times expected value of B. And also we have another term if they are not independent, okay. We have covariance between A and B. So that's why here we have covariance between A, B. This is estimated here, A with B. A with B is a covariance between A and B. We can name it covariance AB. So we need to add this part, and then together we have the indirect effect. This is the expectation of A times B. And then we have the output. So that is a code. And after you run the code, we have the output. Let's look at the output. We have within level. Okay, so again, we have, how can I remove this bar? Okay, we have within level, we have between level. Okay, within level, residual variance, because we have M and Y. These are 2 dependent variables. Residual variance of M and Y. Between level, A with B, what does that mean? This is a covariance between A and B. This is the covariance between A and B, okay? And also we have A with C prime, because in the previous statement, we were trying to estimate the covariance between A and B, A and C prime, and B and C prime. All of these are, covariance are provided. And the mean, the average, mean of the intercept of M, mean of intercept of Y, mean of A, mean of B, mean of the C prime. So these are values. And the variance, okay, variance of M, variance of Y, variance of A, variance of B, variance of C prime. And then we have the newly defined direct and indirect, okay, direct effect, which is C, okay, C prime actually. Yeah, so we have the estimate of C prime, okay, C prime, yeah. And indirect effect is A times B plus the covariance between A and B. So this is estimated here. And the p-value, okay, p-value is significant. P-value is almost 0, so it's less than 0.5. It is significant. So we can see that there's a significant indirect effect, although it is a multi-level mediation. It is still significant. Okay. That is one case in the multi-level mediation, okay? But we have some other examples. For example, in this case, the X here is between, the X here is located as level 2 instead of level 1. So this is another case. And in this case, this A should be constant because here, the X value is constant within each level 1 unit. Okay, because X is level 2. For example, think about this is the individuals in the same classroom. Okay, and this here we have different classrooms. For the same classroom, we share the same instructor. Okay, we share the same textbook. So this coefficient is constant because this is constant for each within each level 1 unit. Okay, so here we do not have random effects. This one is fixed. This one is fixed. But here could be random because M and Y are at level 1. So by looking at the different classrooms, we may have different B's. So B here is a random variable, but not A and C prime. These are fixed because X value is fixed within this group, okay, level 1 group. And we may also have this model, okay, although X and Y is the same level 1, but we can make it constant, okay. We can make it random or make it constant if it's level 1, if they are at level 1. We can also add some other variables at level 2. For example, W here gonna moderate this mediation, moderation, okay. So we have moderated mediation here, and W is a level 2 variable. So they will influence the random effects of B and C prime. Okay, so we just give an example of multi-level mediation, and let's look at the longitudinal mediation. So I don't think we finished everything today. That's okay. So next time we can, if we have the workshops, we can continue this part. Longitudinal mediations. Sometimes the previous cases we didn't consider time, but sometimes time is important. Okay, so because these are examples of mediations with temporal sequence. So we have different time points. For example, poverty and effective parenting and the child maladjustment. So we have different time points. So the effect will be different. So marital conflicts causes emotional security and children adjustment. So if we use the sequential design, so for example, this is sequential design, X measured X, M measured at T plus 1, different time points, and Y is measured at T plus 2, again, different time points. If we just use this mediation model, of course, we have some result, but that result are not accurate because we didn't consider the time points. Yeah, so we have some research articles talking about the bias. So if we use an autoregressive longitudinal mediations, then you will have some bias if you use a traditional. If the true model is autoregressive longitudinal mediation model, but if you use a traditional mediation model, the estimate will be biased. For longitudinal mediation, we have some assumptions. Okay, stability, stationarity, equilibrium. So we have assumptions for longitudinal mediations. And this is example for longitudinal mediation. In this case, it's a complete mediation. So we still have X and Y. And we have time point 1 measures. We have time point 2, time point 3. We have different time points. We have measures of these three variables. And from X1 to X2, actually, we have some coefficient. We assume it's autoregressive. So we have some coefficient from X1 to X2. So all these variables will be different when you measure it at different times. And if you want to write the equations for this model, then you can have this. Okay, so mi at t plus 1 will be influenced by the previous m measured at time t and x variable, because it is mediation. Okay, m will be influenced by x and also the previous m. And of course, these are coefficients. And y will be influenced by previous y, okay, and n. And of course, we have some x, but because it's a complete mediation, we just ignore. See here, we do not have the direct effect because it's a complete mediation. So we ignore the C here. Of course, we have the partial case. In that case, we have the C, the direct effect here. So in this case, that y is influenced by previous y and m and x, but x, m are measured at different time. Okay, so this makes the longitudinal mediation complicated. So we have complete mediation, we have partial mediation, and all of these are longitudinal. Okay, but if you use a traditional mediation analysis models to analyze the data, or cross-sectional, sometimes people call it cross-sectional mediation models to analyze longitudinal data, longitudinal mediation data, then there will be a lot of bias. And yeah, so the research articles shown that there are some bias. The results are incorrect. The conclusions are incorrect. Okay. So Maxwell and Cole provide this C prime. Okay, this prime. This is a solution of the C prime. Yeah, of course, we have A, B, X. All of these are defined in this model. Okay, A, B, X, M. And we also have the autocorrelation. Okay, so rho between time X and the time T minus 1. So these are autocorrelation between X at time and T and T minus 1. This is another autocorrelation between, okay, we have this C prime. So if you have the complete mediation, the C prime should be 0, but if only happened when these two autoregressive are the same, then C prime 0, then we have a complete mediation. Otherwise, you have not complete mediations. Okay, so if they have different conditions, the C prime will be different. So the true model here is a complete mediation in this case. But if you use a traditional cross-sectional mediation, you will have the bias. Okay, the C prime is not 0. Okay, unless these two is equal, then you have the complete mediation. So this showed the bias exists, and also the bias in the partial mediation. That is the C prime. Okay, it's not the same C. And also we need to consider time, okay, timing of time. So for example, this is a true model. Okay, so suppose we have different time points. And if you just measured at time point 1, time point 5, time point 9, then you have different legs. The different legs will also cause different results. And the bias will, yeah, there will be bias. Okay. Yeah, so the legs will also influence your result. And based on the Warren's paper, we have some information about the timing. Okay, by using different times, the legs will, when your legs will be is different, the results will be different. And yeah, so this is an example of the active data. So again, by using the previous example, we have reasonability, we have the XM. Okay, XM is a reasonability, and Y is a everyday problem solving. X the control. Okay, now in this case, X the control group or reasoning training group. So we have different X, different groups. We have these different abilities. We have different EPT values. So we can have different models for the same data set. We may have this longitudinal model. Okay, we may have this longitudinal model or this model. Okay, in this case, we have different time points. Okay, we have baseline measurement, we have after 6 weeks, 1 year later, 2 years later. And we have initial training, we have booster trainings. So for each model, you can just have the chi-square, the relative chi-square value, the AIC value, BIC value, and the RMSEA. So by running these different models, you can just pick the best model to fit your data. And we may also have half longitudinal data. So in this case, so it's not 3 time points, it's 2 time points, it's half, okay? So in the previous case, these 3 variables here, 3 variables are measured 3 time points, okay? X and Y, but you can also have half longitudinal cases. So in that case, we have 2 time points, okay? And we can have this longitudinal design. So we have control group, we have intervention group. Okay, the X variable here is the variable either 0 or 1. Okay, control variable 0 and the intervention variable group 1. And that will influence the M value and the Y value. Yeah. And for Y here, for Y, so it's longitudinal, so it's gonna influenced by M, by previous Y, and also the I, the control or treatment group. And N, yeah, so that is for the Y variable. And M will be influenced by the previous M and the intervention or control group design. And we can also have a longitudinal other latent growth curve longitudinal mediation. So in this case, we have M here. Okay, M is observed. We can have some latent intercept and latent slope. And the Y dependent variable, we can also have latent intercept, latent slope. And then we look at the mediation of these latent variables instead of the observed variables. Okay, X is independent variable here, and X will be influenced the latent slope of M, and which will influence the latent intercept slope of the outcome of Y. Okay, this is actually the latent growth curve model, but this part is mediation. Okay, but of course it's longitudinal because we have so many waves. We have intercept, we have slope. Okay, so it's longitudinal. So we may have many other longitudinal designs. That is a differences between the autoregressive model and the longitudinal latent growth curve models. And we have some other mediations, for example, causal mediation models or network mediation models. Okay. But now it's 11:10, so I cannot finish everything here. So these are advanced topics. So if you're interested in these topics, you can also Google online. There are a lot of like videos talking about these topics. So I think that's it. So any question? Sorry, 10 minutes past 10. Okay. So if you have any question, you can also send email to me. Okay, that's my email address. Any question? Okay, now it's really late, 11:10. Maybe we should stop here. Okay, again, thank you for attending the workshop of ISDSA. Okay, thank you.
Thank you, Professor Wu.
Thank you.